In this video, we're going to discuss finite difference theory. It's really less of a theory and more of a method or a technique in which you'll use some skills that you already have in order to find a clever way in order to problem solve. Let me show you what I mean. Let's say you have a sequence like a sub n equals, and the first term in the sequence, oh, maybe it's 7, and then the second term is 14, and then the next term is 24, and then after the 24 comes 37, and after the 37 comes 53. And you're trying to determine maybe an explicit equation for this particular sequence, and you're a bit stumped. You can tell that the sequence is not arithmetic because the difference between 14 and 7 is different than the distance between 24 and 14. Meanwhile, it's also not geometric because the ratio between 14 and 7 is different than the ratio between 24 and 14. However, if you spend a little time examining the pattern on a deeper level, you might uncover something interesting. For example, if I look at the differences between terms, I see that to go from 7 to 14, I go up 7. And from 14 to 24, I go up 10. And to go up from 24 to 37, that's an increase of 13. And then finally, I see an increase of 16. Not a common difference. And that tells me really nothing other than this is not an arithmetic sequence. Well, one thing that we know about an arithmetic sequence is that it's actually linear. And that is to say that a sub n, the nth term, is simply the first term plus n minus 1 times the common difference. That n right there is raised to the first power. Well, if I look at not just the differences, but the differences of the differences, so from 7 to 10, I go up 3, and then that's constant on the second one here, and then 3 again, this indicates to me that this is actually going to be the original sequence, that is, a quadratic sequence. Not arithmetic, but actually some second-degree polynomial. To put a definition to this idea, I would say this. The theory of finite differences is a method that will allow you to find an explicit formula for any polynomial sequence. Let me show you how it works, and then we'll put it to work with a few examples. There's really just 3 steps in the process. In the very first step, all you need to do is examine the difference between successive terms of the sequence. In the second step, recognize that the level at which a common difference is found tells you the degree of the polynomial sequence. So if you find a common difference at the second level, it's a second-degree sequence, a quadratic. If you have to go to the third level, it could be a cubic sequence. Of course, sometimes you'll never find a common difference, and that just tells you that it's not a polynomial sequence, because the method works specifically for any polynomial, quadratic, cubic, fourth degree, and so on. Our third step is to go back to old algebraic techniques that we've learned previously and that we can review to help you find an explicit equation once you know the degree of the sequence. Let's see it in action. Our first example is a very interesting problem. It says, the chefs at the Lazy Pizzeria cut their pieces in such a way that they get the maximum number of slices for a given number of cuts. As seen in the picture, with 1 cut, they can get 2 pieces. 2 cuts produces 4 pieces, and with 3 cuts, they can produce 7 pieces. First, we are asked to show where you can place a 4th cut so that 11 pieces result. So if I could just zoom in on this image right over here, as you can see, there are 7 different regions created with those 3 cuts. I need to add an additional line. I need to figure out just the right spot to add that additional line so that I end up with 11 pieces. Pause the video and see if you can come up with a good spot to add the line. Of course, there isn't just one right answer to this problem, but one possible position that you can place this cut to produce 11 regions would be right through here. I can show you that with just some careful counting. Here I have one region and then another one. Here's a third. Here's a fourth. A little tiny one here. It's a tiny slice of pizza there. 6 here. 7 there. I've got 8 and 9. A couple tiny little pieces there. Here's 10, and the last one right here is 11. And like I said, you can vary that red line a little bit. You might end up with less than 11, but you can never come up with more than 11. And so now we're asked to use finite difference theory to determine the maximum number of pieces that would result from n cuts. Just missed the little n right down here in the statement of the problem. So we want to come up with an explicit equation for this. So it might be good to begin by organizing our information in a table. So let me organize the information that we gained from counting some basic cases into a nice table so it's easy to follow. We saw that if there was 1 cut, the pizza would be sliced into 2 pieces, and then 2 cuts sliced into 4 pieces. And then things got weird when you had 3 cuts, because you could slice into more than just 6 pieces. You could slice into 7 if you put it in just the right spot, and then 4 cuts sliced into 11 pieces. If we analyze these differences using finite difference theory, we see that it increases by 2, then it increases by 3, and then it increases by 4. And thus we don't have a common difference, and it's not a linear sequence. It's not arithmetic. It also isn't geometric. What it is, in fact, since there is a common difference at the second level, it tells us that our sequence is quadratic. So here, once I know that my sequence is quadratic, I can start adding some variables and specifying exactly what the sequence might be. Let's say I let the number of cuts equal n. So I'll let this be the variable n. And then the max number of slices, I'm going to use m for max sub n, because it's a function of the number of cuts that I make. What I know at this point is that m sub n is a quadratic sequence. That means it needs to look like an squared plus bn plus c for some parameters a, b, and c. That's from this information that I gain right here from the theory of finite differences. Now, this is really all speculation at this point, because I haven't counted 5. I don't know for sure that it's quadratic, but this is a really good problem-solving tool that works more often than not. And so, from this information, I'm going to write some systems of equations. I have some ordered pairs in my table, like right here. This is an ordered pair, 1, 2. The input, the number of cuts is 1. That's n is 1, then m is 2. When I plug that information, that ordered pair, into my general form that I discussed right here, m equals an squared plus bn plus c, I get 2, the number of cuts, equals a times 1 squared plus b times 1 plus c. My second ordered pair right here is 2, 4. When I plug this in, I get 4 equals a times 2 squared plus b times 2 plus c. When I plug in another ordered pair, this one here is 3, 7, I get 7 equals a times 3 squared plus b times 3 plus c. Now I'm just going to rewrite that system of equations a little bit nicer, evaluating the squares and writing coefficients in front of variables, and that'll give me this. Now you'll notice that I never bothered with this fourth ordered pair right here. That's because a quadratic equation is defined by exactly 3 parameters, a, b, and c. And in order to solve for those 3 unknowns, I only need to write 3 distinct equations. If I was working with a cubic, then I would need, at the very least, a 4th ordered pair in order to solve the system and find the unknowns. In terms of solving the system of equations, one thing that I like to do is I like to number my equations 1, 2, and 3. And then this particular one has a really nice structure. And in fact, you'll see this happens a lot. If you take equation 2 and subtract equation 1, you come up with, let's see, it'll be 4 minus 2 is 2 equals 3a plus b. Meanwhile, if you take equation 3 and subtract equation 2, you get 7 minus 4 is 3 equals 5a plus b. Notice that both of those eliminated the parameter c. So now I have these new equations. I'll change color once again, maybe number them 5 and 6. And this time, if I take equation 6 and subtract equation 5, that's so easy. I can eliminate the parameter b. 3 minus 2 is 1, and 5a minus 3a is 2a. And therefore, I can conclude that a is 1/2. Back substitution into equation 5, if a is equal to 1/2, then b is equal to 2 minus 3/2, which means b is also equal to 1/2. And then back substituting that all the way maybe into equation 1, if 2 is equal to a plus b plus c, then 2 is equal to 1/2 plus 1/2 plus c, and therefore c is equal to 1. And this gives me a lovely little quadratic equation for the maximum number of slices, 1/2 n squared plus 1/2 n plus 1. And so, if you were curious, how many cuts would it take for 5 slices? Well, you do 1/2 of 5 squared plus 1/2 of 5. So that's 12.5 plus 2.5, or 15, plus 1. And that tells us that we would end up with 16 slices. And you can see that that would be consistent with the pattern that we saw, plus 2, plus 3, plus 4, plus 5. And it continues to fit that pattern. Though I don't think you'd want to go back and try to draw for 5 cuts, because it starts to get pretty crowded. Let's take a look at another example. In this example, you're asked to imagine a large cube with a side length of 17. It's painted on all 6 faces, and then it's cut up into 4,913 smaller cubes. And in case you aren't aware, 4,913 happens to be 17 cubed. So you can see in the diagram here, it's cut up into all these little 1 by 1 by 1 cubes. And the question that we're asked, actually there's many questions to this problem, it says how many of these smaller cubes will have paint on 3 faces, 2 faces, 1 face, or 0 faces? This is not an easy question at first, but as you start to dig into it, you'll start to see some very, very interesting patterns emerge. I encourage you to pause your video and see if you can figure it out. Okay, so first the answers and then the explanation. You'll find that there are exactly 8 cubes that have paint on 3 faces. For 2 faces, there are 180 of the smaller 1 by 1 by 1 cubes that have paint on 2 faces. There are 1,350 that have paint on 1 face, whereas with 0 faces, there are 3,375. So let's see where those answers come from. One thing's for sure, and that's that these finite difference theory problems are really exercises in problem solving. It's not a specific mathematical skill that you need necessarily. It's the ability to organize your work, put it together in a nice organized table, or solve some simpler problems, figure out some basic cases. Those are the types of things that will lead to your success in finite difference theory problems. And in turn, finite difference theory will help you become a better problem solver. So here we look at the painted cube problem that we mentioned. I've organized a table here in which I've varied the size of the big cube. We'll consider a 2 by 2 by 2 all the way up to a 6 by 6 by 6. As we look for patterns, we'll keep track of total cubes as well as cubes with 0, 1, 2, and 3 painted faces. And of course, just to make this analogy work a little bit better, maybe to have a better picture in your head, instead of thinking of painted cubes where we paint the outside of the cube and then cut it up, it might be easier to think of various size Rubik's cubes. So I have pictured here a 2 by 2 by 2 and a 3 by 3 by 3 and a 4 by 4 by 4 and a 5 by 5 by 5 Rubik's cube, where we can think of how many of the little cubes have 0, 1, 2, or 3 stickers on them. Of course, that goes with the assumption that a Rubik's cube is not hollow. So we're really still talking about the painted cube problem, but we're going to use the Rubik's cubes pictured here to help us visualize how many would get painted. Since the stickers only go on the outside and the paint only goes on the outside, the two questions are essentially equivalent. So let's start with the 2 by 2 by 2 case. So I'm picturing this cube right here. And of course, since it is a 2 by 2 by 2 cube and 2 times 2 times 2 is 8, I know I'm dealing with 8 total cubes. Also, I can see that all of the cubes, all 8 of them, meet on a vertex. That is to say, on one of the corners of the cube. And on the corners of the cube, you can always see 3 different colors coming together. And in the case of the one that I circled there, I've got red, white, and blue. Every single corner has that case, and there are 8 corners. And that is to say that all 8 of the 2 by 2 by 2 cubes have 3 painted faces or 3 stickered faces. So I can fill zeros in the rest of the column. In fact, I also noticed that when I go up to the 3 by 3 by 3 cube, I still see on the corner, right on the vertex there, the red, white, and blue coming together. And that's the only spot that I'll see the red, white, and blue coming together on those corners. And it doesn't matter the size of the cube, it's always going to have 8 vertices or 8 corners. And that is to say that I can fill in 8s going right down the column here. You can see even in the 5 by 5 by 5 cube, right? Only on the corners will I find those 3 stickered cubes, so to speak. Okay, well, what else can I figure out from my table here? I guess I could quickly figure out the total number of cubes, right? A 3 by 3 by 3 should have 3 cubed, or 27. A 4 by 4 by 4 should have 64, then 125, and then 216, right? So if I only have accounted for 8 of those 216 in the 6 by 6 by 6 cube, I got some work to do. I've got some pattern detecting that I need to figure out. So let's go back to that 3 by 3 by 3 case. And let's think about how many have 2 painted faces, 1 painted face, and 0 painted faces, and see if we can make some sense of it. For the 2 painted faces case, I can see one right here. Here's a cube with a red and a white face, right? And I see that that occurs on an edge. And there's another one here. It's red and blue. There'll be another one back here, right? It might be red and orange or red and yellow. And then there'd be another one here. And of course, there would be 4 more on the bottom, right? Because they're going to occur on every edge, 1 on each edge, and there are 8 edges. So, I'm sorry, there are 12 edges. Not only the 4 on top and the 4 on the bottom, there are also the 4 lateral ones that I almost forgot about, right? These 4 along the middle. And so there will be 12 2-sticker cubes on the 3 by 3 by 3. Okay, well, what about cubes with only 1 painted face? Where would you find those? Well, I can see one right here. It's a red one. I can see another one here. It's a blue one. I can see one right there on the front. It's a white one. Oh, actually, you can see one on every single face, and there are 6 faces. And so I'm on my way. Well, that leaves us with the 0 painted faces. And this is where the Rubik's analogy falls apart, because the Rubik's cube is actually hollow, but an actual cube wouldn't be. And there would be some cubes on the inside that would not get any paint whatsoever. How many would there be? Well, I mean, it's not a mystery anymore. I know that whatever this number is right here, x plus 6 plus 12 plus 8 must equal 27. And that allows me to say that, well, I guess x is equal to just 1. And if you think about that a little bit, if you think about your cube almost like an orange or something that you'd have to unpeel, after you unpeeled the cube, there would be another cube inside. Like when you peel the spherical orange, it's still spherical. Well, how big is the cube? Since I took a layer off the top and a layer off the bottom, the cube has gotten 2 units smaller than it was before. Instead of 3 by 3 by 3, it's 1 by 1 by 1. And so what I'd like you to do next is consider this picture here of a 4 by 4 by 4 Rubik's Cube. If you actually have one at home or something like that and you can use it, that's fantastic. If not, try to picture it in your head. Try to see if you can figure out how many cubes would have 0 painted faces. How many would be inside if you kind of let all those little 1 by 1 by 1 cubes fall out? How many would have 1 painted faces? I see 1 right here. How many more would you find? How about 2? Right? Can you figure out the rest of this row? If you've got that down and you're looking for a challenge, see if you can figure out 5 by 5 by 5 and 6 by 6 by 6. Take a minute, pause the video, try to count up the rest of the table, and I'll be back in a second with the answers. Okay, so here's our table all completed. And one thing that you can do to always check your work to see if you've counted things right is, of course, you can add up any particular row. 64 plus 96 is 160, plus 48 is 208, plus an 8 is 216. So everything seems to check out. What we're asked to do is to eventually come up with an equation in terms of the size of the cube for how many have 0 painted faces. How many have 1? How many have 2? How many have 3? Because ultimately, the question that we were asked is, what's the deal with the 17 by 17 by 17 cube? And so I want to show you, without showing all the different details, how finite difference theory can help you with that sort of thing. And essentially what this problem has to do with finite difference theory. So for starters, let me say that a sub n is equal to the cube with 0 painted faces, and then b sub n is 1, c sub n is 2, and d sub n is 3. I'll start with d sub n as a sequence because that is the easiest. D sub n is this constant sequence, 8, 8, 8, and so on, right? Just like that, it's a constant, it's always 8. So an explicit formula for d sub n is d sub n equals 8. Of course, with the caveat, and this is an important caveat, that n must be greater than or equal to 2. You know, in fact, it might be better for me to kind of put maybe right here in this place, right here where the very first 8 was, maybe I just put an NA. What? Why am I saying that? Well, we don't start with a 1 by 1 by 1 cube. So if I'm going to define n as the side length of the cube, well, my sequence doesn't really start, my pattern doesn't begin until n equals 2. And that's not too uncommon with problem solving. Sometimes the pattern doesn't get going until a few terms. Let's move on to c sub n. So c sub n is the next simplest. I realize I'm going in reverse alphabetical order here. Still doesn't apply for n equals 1, but then I get cube with 0 painted faces, and then 0, and then I get 12, and then I get 24. Just reading the numbers all from the column right here. As we can see, this is arithmetic, right? This is arithmetic. It's going up by 12 each time. The common difference, in fact, is 12. And so I can say c sub n equals, well, the first term, if it existed, would be negative 12, right? And then plus the common difference of 12 times n minus 1. Or if you feel like simplifying all that, it would just be 12n minus 24. And again, this would take into account once n was greater than or equal to 2. So we've seen a constant sequence, we've seen a linear or an arithmetic sequence. As I move on to b sub n, I think you'll see what I'm getting at here, right? Starts with doesn't apply for the 1 by 1 by 1 case. Now my sequence, just reading off the terms in this second column here, go 0, then 6, then 24, then 54, then of course 96, right? I examine this sequence. I don't initially see anything going on. I notice then it goes up by 6, then it goes up by 18, now it goes up by 30. Okay, what's going on here? Up by 42, right? If I look at the differences of the differences, I see it goes up 12, then 12, and then 12. And this tells me that B sub n is a quadratic sequence, all right? So then B sub n, I can be sure, right? I can be sure that B sub n is going to equal some kind of quadratic equation. And you can use the technique that we saw in the last example to come up with the quadratic equation. Or, and this is important, if you're paying a close attention to the geometry of this problem, you'll notice that the cubes with one painted face only occur on the actual face of the original cube. And there are only 6 faces on the original cube. So let me just demonstrate by drawing this one here. And these happen on the face. And they're always in a square. And the size of that square is always 2 units less than the length of the cube. And so 6 times n minus 2 squared would be the equation that you would get at the result of finite difference theory, the solving the system of equation that you get for B sub n. Let's wrap things up with A sub n. A sub n, of course, as a sequence. Puts a nice ribbon on this. Doesn't apply for the 1 by 1 by 1 case. And then we have 0, 1, 8, 27, 64, and so on. We can see it goes up 1, goes up 7, up 19, and then up 37. No clear pattern there. But if we look at the next level, we see 6, then 12, then 18, and a pattern begins to emerge. It completes itself in the third level. I got a plus 6 down here, and this tells me that A sub n is in fact cubic. And of course, if you've been paying attention to the geometry, it makes perfect sense. Inside the cube, when you unwrap the cube, you get another cube, just like the orange. That cube is exactly 2 units smaller than the original. So if you use finite difference theory to try to come up with the equation that we saw there, you'd end up with n minus 2 to the third power. And that is a nice example because it shows sort of the power of finite difference theory. All of these patterns, A, B, C, and D, all of those sequences were different. Linear sequences, constant differences, cubics, quadratics, they were all over the place. But in the end, finite difference theory could figure them all out because they were all polynomial in nature. And there are a lot of patterns out there that are polynomial in nature. So understanding this technique and looking and thinking about trying to use it, counting basic cases and organizing your work is an outstanding problem-solving technique. So in conclusion, the big idea of finite difference theory is that you don't need to memorize any kind of special formulas to figure out explicit equations for polynomial sequences. You just need some algebra skills, and then maybe even more important that you need some willingness to problem solve, to take a problem, break it down to simple components, organize your work, and build up to something bigger. Thanks for watching.